Good evening, everyone, and afternoon also. Welcome to our seminar for today, where we're being presented by Pilani Viela, who is one of our PhD students, and he's looking into feature selection for regression in machine learning models using REPA methods. And with the use of big data, we fall into the challenge of dimensionality, of which sometimes there may be some columns which may be correlated, and it becomes redundant to use every column on there. So Pilani is going to be discussing with us some of the REPA methods that are being used in terms of dimensionality reduction. I'll hand over to you, Pilani.
Okay, thank you, Emmanuel. Good afternoon, everyone. So today I'll be presenting on this concept of feature selection using REPA methods. It's something I was playing with. I think and last week Emmanuel asked me to present. I thought I'd just present on it. I think the aim for today's presentation was to show the methods and also show some of the results from the data set I was playing with. But then, these methods do take some time. I did do some simulations and I expected them to come through. I started them over the weekend, but it looks like they're not concluded yet. So I don't know, maybe we can discuss later, maybe as part of next week's seminar. I know someone will be presenting. I could use maybe like a 10-minute segment just to present some of the results from the data set that I was working with. Okay, so in feature selection is a big component in developing data-based models, specifically machine learning models. If you look at the whole machine learning pipeline, when you develop this database model, you have your data, then you sort of prepare your data. And that means cleaning the data, getting a data set that is representative of the system that you're modeling. And then normalization, that is normalizing the data, maybe using 0 to 1 scaling or using Z normalization based on the characteristics of the data, and whether you're using it for you're modeling a classification problem or a regression problem. Preparation also includes transformation. Common methods are singular value decomposition. I think someone's mic is on. They could please mute it. If you could all just check your mics. Okay, thank you. So transformation involves representing a data set in a different sort of state space. Common methods are principal component and analysis and singular value decomposition. There's also the validation, which I've said, that is validating your data set and ensuring that it's representative of the data of the system that you're modeling. And then the main topic that I'll be talking about is featureization. So featureization is a concept that is different from transformation, where you are basically, you have this Y value that you want to model that's based on a set of X values. And these X values are called features, and you want to select the features that best describe this Y value. And then it is after this step that you can actually take once you've gotten your data set, gotten the features that are representative of this output variable that you want to model, and that it is only after that step that you go ahead and start building and training your model. And featureization is what we're going to be focusing on. And it is a bit of an issue. So, looking at, most of us are in a chemical environment. In chemical processes, there is a good foundation in terms of first principles, whether it's separation processes or reactor processes and so forth. So from our fundamentals, we can sort of scope and see, like, okay, for reactor temperature, we know that conversion and maybe concentration, they are sort of good predictors of that. But over the past couple of months, particularly in an industrial setup, you have these processes that have been in existence for like 30 or 40 odd years. There have been so many changes and updates to these processes to a point where and some of them are so complex that you can't just jump from your first principles models and select features to represent your target variables. So, and this is where these methods will come into play. They aim to sort of make, without having first principles knowledge of a system, you could use them to select the best set of features that are representative for a particular output that you're trying to model. So just to go into deeper, what is feature selection? So it is a process of selecting a subset of relevant features to use in a machine learning model building. So if you look at this diagram, you have all your features, and it's basically, you have all these features that you're using to model a Y value. So you can look at these as sort of X values, and you want to select the best set of X variables that will be best representative of your Y variable. It's used in many domains, computer vision, in unsupervised learning. So in these different fields, it has different names. So it also can be known as variable selection, attribute selection, and also subset selection. So if you see these terms, it's basically the same concept. And it really has, the ability to select the features that are most representative of this Y variable that you're trying to model really can have a significant impact on model performance. Performance in terms of the amount of time taken to build a model and train a model, and also in terms of how well your model can predict for this variable that you're trying to, Y variable that you're trying to model. And it has become a key aspect in machine learning models for making machine learning models that are robust and reliable. Another important point, sometimes we can tend to confuse this with feature engineering. Feature engineering is a different concept where you create a new feature from the ones that are already existing. So for example, if you are modeling, let's say a distillation column, then there's this concept of distillate to feed ratio. You can engineer that feature into a model. It can be either a ratio, a summation, or sort of any analytical relationship between the features to develop a new feature. So now the question you may ask yourself, why don't we just let the machine learning model decide? For example, a typical artificial neural network, it's based on weights, and you train these weights based on how they can predict your Y value. And if you have a feature that really doesn't have an influence on your Y value, that weight will just be a very low value. And your machine learning model can actually predict, even though you can give it, or without even doing this feature selection. But there are a lot of benefits to going through this approach of feature selection. First thing is the concept of the curse of dimensionality. And I'm sure if you've worked with the data, this is one of the first things you're going to come across. The concept of curse of dimensionality is that once there's a significant increase in the feature space, it results in the number of possible configurations growing, exponentially. And as a result, so if you take let's say you have a data set of 1 million points, and you take maybe a sample of 100,000 points to model that data set, that set of 100,000 points, it will be very difficult for it to be representative of this high dimensional space. So as a result, for you to, the number of configurations that need to be covered by observation, you need a much larger data set to cover all these combinations. And then there's this exponential relationship where even increasing by one feature can result in you increasing your data set by the order of like 10, in my experience. Another reason why we wouldn't want to just shove all our features to a machine learning model is because when we build models, we want to build a model that is, firstly, that is simple and interpretable. So if your model can be interpreted and you can explain what it does and how it predicts from your set of inputs, it makes it explainable, and also you can also makes it easy for you to diagnose and improve on that model. And the concept is, the more, if you have like 100 features for modeling a particular Y value, then it becomes very difficult for you to explain your model. And in instances where it starts deviating in prediction, it'll be very hard for you to identify the problem and diagnose that. So with feature selection, we are able to have a simple model that we can actually improve on and diagnose. Another thing is, yes, with machine learning, you have these very powerful tools that you can use, to draw predictions from data. But how good your prediction is dependent on how good your data set is. And in large data sets, you do have these redundant variables. In some, it can just be like a name or ID variables that actually have no impact on your output variable. But in the prediction process, they can actually influence how your model predicts, and in most instances, it reduces the prediction accuracy. So having these redundant features it drops the quality of your data set. And then if you have a poor quality data set, then your output as well will be of a poor quality. And also the last point is relating as well to the cost of dimensionality. A large feature space results in a complex model, and the more complex your model is, the more significant the amount of time will be required for you to train that model to predict well. So now, just to now that we've sort of seen some of the benefits, just to summarize, feature selection, it reduces the number of features to be those that are relevant for the output. And this makes building the model much easier, makes your model to be simplified, making it easy, much more simpler to debug. You can actually come to a point where you can actually interpret your model and how it's behaving with respect to the different variable. And through the efficient selection of relevant features, that you reduce the model training time and also improve the model performance. Now, just to go through the common feature selection methods. So the first one is filter methods. So it's the two main ones. I'll be just talking about the filter methods and the wrapper methods, but then I'll go much deeper into the wrapper methods. So the filter methods, I think we are all sort of familiar with it. It's basically, there's a metric, and the metric is based on the features characteristics without using a machine learning algorithm. So you have a set of X values and you have a Y value, and you develop a metric to determine how the X value is, how good a predictor the X value is to the Y value. And based on that feature, you select whether this X value is this feature is a good predictor or not. The filter methods, they're very quick to calculate because it's just an analytical, it's a simple calculation. They are good for quick screening and removing of irrelevant features. The common ones are the Pearson's correlation. That's that's more for linear systems. So through Pearson's correlation, you take a feature and you draw up the correlation with the Y value. And if it's closer to 1, then it's or closer to 1 or -1, then you determine that there's a strong direct relationship or inverse relationship. Another common one is the Spearman's correlation. Because Pearson's is only for linear, Spearman's tends to accommodate some nonlinear processes, but correlations, but it's not very effective. So even though these, these two are common for regression, but they are not very good for, how can I say, for drawing relationships for highly nonlinear processes. So if your relationship between your feature and your Y value is very nonlinear, then these methods don't serve as really good indicators. And also, these methods are you comparing each feature to the Y value, but then in some instances, you can also cross-reference each feature to another feature. So if you have two features that have a very strong Pearson's correlation of 1 or -1, then basically they are correlated, and then you can sort of eliminate one of these. So now for highly nonlinear methods, the filter methods, they are just well known to be not very good sort of predictors of a correlation between your X value and your Y value. So the wrapper methods are sort of an approach that we can use to resolve this. And this involves, it's selection of the selection of a feature here is taken as a search problem. And how we do the search is that, you have all your features, and then after that, you select a subset of the features. Then using that subset, you actually train your model, your machine learning model. It can be the actual machine learning model that you'll be using in the end, or it can be a simplified version like a surrogate model that you could use just in the time being to help you identify the correlation. So it doesn't necessarily need to be your final model. It can be a much more simpler model, and you can use that as a reference model to evaluate how good your features are in evaluating your final Y value. So the features are used, there's some training, and then it's evaluated. And then after that, you go back again and you select another subset, and then you train again. So this is an exhaustive approach, because if you have, for example, 3 features, so you're going to try the first feature, first and second, first and third, second and third. So already you have like maybe 6, trainings that you probably, a minimum of around 6 trainings that you're going to have to do just to determine the optimal feature set. So, and then how this optimal feature set is determined, you basically have to specify a performance. So you will do variations until you find a variation that has the maximum model performance. But then, because it's a search method, you add 1 by 1 or remove 1 by 1. And then in that case, you add until the performance decreases, or you keep adding as the model performance increases. And then if it stops increasing by a specific threshold, then you won't, I don't know why it's, okay, so you won't, you won't keep adding. And also maybe you have a predefined number of features that you want to set. So if it's a 5 features, you have total of 5 features, then you want to select maybe just 3 out of the 5 to be, and you want to use that as your predictor. So you want to choose the best 3 out of 5. So this approach, as you can see, the bigger your total feature set, the more computationally expensive it is going to be. But then it does provide the best performing feature subset for the given machine learning algorithm. And one of the reasons why it also, it detects interactions between the X value and the Y value, and it also allows you to detect interactions, nonlinear interactions between the X values themselves. So that's where the benefit comes here. So the common search methods using the wrapper approach, there's the forward feature selection approach. So this one here, it starts with no feature and you can keep adding one at a time. And then you also have the backward feature elimination. So here you start the other way. You have all your features, and then you keep removing one until you reach your threshold for your model performance. Then the exhaustive approach that involves trying all possible feature combinations. That can be very significantly computationally intensive. Then there's also the bidirectional search, where you perform the forward feature selection and backward feature selection simultaneously until you get one unique solution. And where this becomes a benefit is because both the forward feature selection and the backward features elimination they are greedy algorithms. So if you, for example, you select your first good predictor, and then it selects, your second good predictor. So you have a combination, but it's already eliminated. For example, if you have 5, you already eliminated the other 4, but then these other 4, these 4 in combination with other variables, they could also produce a much better, prediction compared to the first one that you selected. So you might miss the optimal solution, and that's what the bidirectional search tries to resolve. So just to take a deeper look at forward feature selection, as I said, so this method starts with no feature and adds one at a time. So for the 5 feature system, it evaluates all these 5 features and selects the one with the best performance. That is, in this case, would be feature 3. Then now feature 3, it does combinations, evaluates feature 3 in combination with feature 1, feature 3 in combination with feature 2, in combination with feature 4, and in combination with feature 5. And then it selects the best performing combination. And then after that, it goes again for the remaining ones. It compares so feature 1 and 3 with 2, feature 1, and then it eventually, okay, here I think I made a mistake with here, but then it's supposed to be with 1. So 1 with 2, 1 with 4, and 1 with 5, and then from here you get the best combination for the 3 if it's 3 out of 5. But then, as I said, this is a greedy approach. So you have feature 3 and 1 in 1. But then here, what if the combination of feature 4 and feature 2 in the second level could have provided a much better? So even though feature 2 alone was not a very good predictor, but then in the second level, maybe if you combine feature 2 and feature 4, you probably would, the combination of these 2 would be a much better predictor than this combination. So that's where, this greedy approach, does not, in some instances, does not give you the best optimal solution, because by choosing, the best possible solution, best solution in each step, you might miss an optimal solution due to that is a result of another combination. So this, you continue this until your preset criterion is reached. So maybe you stop here after you realize, if you realize at this point that, adding all these combinations do not actually improve on my performance when I'm in this level, then you'll actually keep these 2 as your 2 features that you're going to use to model your Y value. Implementation. So there is, the reason why these are called wrapper methods is because, in Python, there's how can I say, there's this methods from the MLX10 library, and these serves as a wrapper. So you just add your model as you add it as a parameter to this wrapper function, and then it will do basically this feed forward selection calculation for you. So it's actually very simple to implement this. So usually you can specify the number of features that you want in your model, and you want to go, it's a sequential forward. Also, there's this floating parameter that I was still trying to figure out what was this about, because when I had it as true, it did sort of improve my my accuracy. You also specify your criterion, how you want to score each combination that you're going to be evaluating. And then also there's this cross, Kfolds also has this Kfolds approach where it within, comparing these two, it'll take different subsets of the data set and do sort of a K-fold cross-validation and get sort of an average value for your performance for this combination. And then you sort of you fit this object to the training data. So basically, you specify this object. This is my model. So here you can specify the size of your model. It seems to work with TensorFlow models as well. And then by calling this fit method, then it starts performing this whole forward feature selection for your training data set and your Y training data set. So it does the training, and then it splits as well the training data set and the test data set, and then it uses that to evaluate. And then as well, then you can get the selected features by calling this, by using the K feature index method from this. So it's very straightforward to implement. Now, backward feature selection, as I've said, so this method as well is a greedy-based search method, and it starts with all features and then it starts eliminating. So here you eliminated a feature, you eliminate one. You start with all, then you eliminate they eliminated the first, okay, here the first as well, and here the fourth, and then you determine which one gives you the best performance or the best increase in performance, and then you use that as your baseline, and then again you start eliminating each one, and then you stop once your performance drops, or either drops significantly or it stops increasing based on your criteria. So you keep eliminating until your final criterion is satisfied. And as well, this also, you can miss your optimal solution, because as well, you eliminated feature one here, and then you've gotten these three features. But then what if if once you eliminated here, maybe feature 1, 3, and 4 could also have been a good combination that gives you the good predictors. So using this as well, you can miss the optimal solution, even though you can get good prediction from your feature set. So it's something that you have to be aware of. As well, it's the same as the last, using the wrapper method sequential feature selector. You just set up your model, you insert your model as a parameter, but then here, instead of forward, you change this to false. Now, exhaustive feature selection, I think this is self-explanatory. Here, you basically try all possible feature combinations. And yeah, this can work well if you don't have a lot of your pool of features is not too big. So this could work well in that instance. But if your pool is if your pool is too big, then doing the exhaustive search, it's an NP squared problem. It's really going to take forever to solve. So so this, you could try this when you have small data sets, but it's not really advisable to use it for a larger data set. So as well, there is in the feature selection library, there is the exhaustive feature selector, and implementing this is just a simple as adding your model and specifying your minimum features and your maximum features and your scoring. So now I looked at some work in trying to resolve the limitations of the feed forward search and back. Not feed forward, forward feature search and backward feature search, because like in a big data problem, I think these are the most practical solutions that you could implement. So there has been recent development. It's called the LRS or plus L plus minus R approach, where instead of adding one feature at a time and missing the optimal combination, by selecting a different feature in the previous step, you specify a parameter L and R, which are integers, and these repeatedly add and remove features from the solution subset. So, for example, if L is greater than R, then that means your LRS starts from an empty set of features. Then you keep adding. So instead of adding one, you add two if L is 2, and then you remove one, and then you add 2 again and remove one, and you sort of do it. It's a pseudo random approach, and the aim is that by doing this you can get back that feature that you might have missed in the previous step. And again, it works the other way. If your L is less than R, then you start with the full data set, then you remove. For example, you can remove 2, and then you can add 1, and then you can remove another 2, another random 2, and add 1 until you meet your criteria. But in this approach as well, it's a meta approach where these are like hyperparameters, L and R, that you have to specify. And there's no theory behind choosing the optimal values for L and R. So you might need to do a bit of experimenting for that. So just to conclude on this, I think after this, I was meant to show some of my results, but I don't have them on hand as yet. But I think this was just a good intro to these methods and showing you how simple it is to implement them. And despite their time and space complexity, they are great feature selection methods. And for significantly large data sets, I think ideally a good approach would be you would use the filter method to remove the real outliers, the extreme non-predictors, and then you follow that up using this approach, and this will help you to sort of reduce computation time. Because if you have 100 variables, and then you can reduce that to maybe like 50 or 40 using a filter method, then you're using the wrapper feature selection, you can significantly reduce your computation time. Now, another thing is, when you go back up to this, so here it's assumed that you have a model already that you're going to be using, and usually if it's an artificial neural network or any support vector machine or any model, that model will have its own hyperparameters that you're going to need to specify. And there's that, the concept of hyperparameter tuning. In artificial neural networks, that is, that is your activation function, that you're going to need to choose how many nodes are in your hidden layer. So, doing that, it can become, this very big experimentation, iterative process. So you try to do featureization, then you come to your model building, then you realize that your model, you try to change your hidden layers and so forth. So it adds another layer to featureization. So now instead of having one model here, you're going to have many models with different activation functions and different number of hidden layers and so forth, if it's an artificial neural network. So this can be very computationally heavy. So, I mean, my approach, how I usually do it is I usually use this not for my final model, but to help me get a feel, because you can have a I mean, here you want to do hyperparameter tuning. You can have a suboptimal model, but then that suboptimal model maybe can predict the best features to maybe what, 60%. So basically you're getting the best you have like the suboptimal solution. But then using that suboptimal, it gives you a good reflection of what are your most relevant features. And then you can use that feature set in your final model building and training process. So yeah, I think that concludes my presentation for today. But I think I feel like there needs to be a follow-up. I think I'll maybe slot it in as part of someone else's presentation where I go through this data set that I had worked with. It's a basic CSTR data set, and show how these methods actually do perform better than just doing the normal filter-based approach. So yeah, that concludes my presentation. I hope it was informative and brought some light into something that could be useful to you. And yeah, hopefully I can convince you more once I actually have some good results. I'd like to hand over to the chairperson.
Thank you, Pilani, for that presentation. I would like to now open up the floor for any questions that we might have for Pilani based off of the presentation.
Yes, Prof. You can go on. Let's see. Emmanuel, can I go ahead?
Yes, please.
Okay. So thanks, Pilani, and thanks for this this is very much core to what we do. So it's great that you've brought this up. And in fact, I was first just some clarity. When you are showing these different combinations and your way of either building up the number of features or breaking them down in the forward and reverse, are you talking about actually fitting the data at each stage? Or is there some other evaluation? Does each stage actually require fitting the data? And if it does, is that a sample of the data? And then what about issues of representativeness?
Okay, thank you very much for the question, Prof. So yes, you're actually fitting. So for each combination, you're actually fitting the data set to a machine learning model. Can be a neural network, artificial neural network, or whichever machine learning model. Now, the other question you raised is a very valuable question, because the data set that you're using to fit is also can play a big impact on how well the features, which are the best features that will model your Y value. So that's where the Kfolds cross-validation comes into play. So how the Kfolds work, so you'll have a data set of let's say 1,000 points. Then that data set will be split into your test data set and your training data set. Then in the training data set, I don't know, I mean, I just need to dig a bit deeper. I think this is where the problem is when you just use these.
Sorry, so that K-folding, that's fine, but that is also, we consider that fitting the whole data set as well. In K-folding, you are splitting, but you are, in fact, that kind of multiplies the effort, because you then have to do it 10 times if, not 10 times, well, depends on how many folds you've chosen, but that's considered to be using the whole data set as well. So when you talk about these wrapper methods, it's not the case that you are taking a sample of the data, you are actually fitting the whole data set each time, right?
Yes, yeah, you are fitting the whole data set.
Okay,
So
the
it's
reason
assumed
I
that you have a
asked,
data set.
yeah,
Yes, it's assumed that you have your data set is representative. You have a data set that you feel is representative of the system that you're trying to model.
yeah. So the reason I was asking is because you could alternatively, right, instead of fitting the whole model to add a feature, you could use the indicators. You mentioned some earlier, like Pearson and Spearman, but you know, I wouldn't think of those in the first instance because number one, they work on only numbers, right? And quite often our classification problems, they might have discrete values which are not necessarily numbers. Even if they are numbers, they might be categorical numbers. So what about indices like the homogeneity, or I'm not sure how to say that word, homogeneity? You know, if you think about like a decision tree classifier, you can get an indicator, and that's one thing also you didn't mention, that you know, you can fit different states to different extents. The accuracy on each state will be different. Well, you did mention accuracy, which implied the other metrics, but if you think about homogeneity in decision trees, you know, that would be a nice indicator which is not dependent on it being a number. And couldn't you use that? So in your step, let's say looking at what you've got on the screen now, you're trying to find that first feature. Wouldn't you just look at all those features and which one gives you the best homogeneity, and then you select that one at that stage instead of footing it in each case?
Okay. Yeah, I think for this presentation, I think I focused more on, you know, on the regression side. You know, that was where I think I did my research mainly on. But yes, for classification, it does actually become, I mean, there are more efficient methods. There are even more efficient filter methods, you know, compared to in the regression. Yeah, I just need to, yeah, I haven't really touched on, you know, on the classification side in quite some time, but yeah, the concept of homogeneity, I think we did speak about it some time ago. Yeah, that can be, yeah, in a classification environment, that can be a good metric that you can use. But in regression, yeah, they tend to not work so well. I mean, yeah, it's almost difficult to implement.
You can make it work through, instead of discretization, you can, another thing is, when you are going to the second stage, right? So let's, looking at those blocks you've got there, you've got the first column, so you've chosen feature 3. Now, when you want to do the investigation on the other features, are you then fitting your model, or yeah, I guess in your case, it's regression, so it's fitting the model. You fit the model, and then the residual, are you, for the second feature, are you trying to fit the residual after fitting the first feature?
So residual in what sense?
So let's say from the first feature, you've you used let's just say it was a linear, you fit a simple linear, like if your variable was x, then ax plus b. So you fit ax plus b in the first column, and it turned out x was feature 3. And then to find the next feature, right? So in the second column there, did you then subtract your model from the first column? So you took data minus first model, and then you got a residual, and then in the second column you are trying to fit on the residual. Is that how this works?
No, I think it's much more simpler. So how, I mean, how it basically works, you're basically adding another fix. So if you have ax plus b, there, let's say it'll be ax1 AX plus B. And then your second one will be, it'll be AX plus, AX1 plus BX2 plus C. But then in your machine learning model now, so
yeah, I think that is footing the residual then. Yeah.
Okay.
Yeah.
All right.
Okay.
I think I'm not interpreting this.
No, that's clear then. Yeah, I just wanted to understand how you, so you're basically doing another fit exercise on the residual. You can either just keep the original data and try and fit it using the old model, or you can subtract that off and fit the residual. So, yeah, but it's effectively the same thing. Okay. So then you do have to do a fit. Yeah, I'm just seeing that it would be easier. You could avoid any fitting. I think you have to fit at each stage, but the approach I'm suggesting here is, what if you use an index and then you identify the best variable, and based on homogeneity or on the other two you mentioned, whatever index. So because just the whole approach, it's quite computationally intensive. So I'm just thinking of an alternative, right? So what if you just identify the best feature first, then you fit the data on that best one. And when I say find the best one, I mean by just using that index. Instead of doing a fit each time, you just use that index, and that's a straight, I think it's order one evaluation. Then you just identify the best feature, fit it, subtract it off from your data. Then the residual, you move that over to the next, you find the next feature. And again, using like homogeneity or something, then you get the next feature. That way you avoid having to fit the model each time.
Okay, so it's basically there's a sub-step.
It's at the end of each stage, you do have to do one fit, but it's not the case that you have to do 5 fits and then 4 fits and then 3 fits. Instead, you're doing 1, 1, 1, and you are just using the index to figure out what the best feature is each time.
Okay. Yes. Okay. Yeah. That could reduce your computation significantly. But then, yeah, it's just a matter of that index that we will use. You know, how confident, yeah, we would be.
So it would be quite interesting to do this as a study, to do it both ways and see whether there's merit in this kind of single step evaluation approach.
Okay, and then if, for example, you know, when you fit in the end, yeah, and then what if your metric doesn't give you, so for example, can you see my cursor? So basically you're saying, so we have feature 3, then we using an index, we compare feature 3 and 1, 3 and 2, 3 and 4, and then that index will give us the best combination, the best performing combination, and then we fit. Yeah,
you would basically reevaluate the homogeneity for each feature on the residual. So from the first column, you've now chosen feature 3, you've gone and fit using feature 3, and now you can calculate a residual. Because you fit it, you've got a residual ready for column 2. Then in column 2, you take that residual and you work out the homogeneity of the features 1, 2, 4, 5 with respect to the residual. And then, yeah, then using that, you can repeat that process as much as you like.
Okay, all right. I think it's something we can look into. And basically when you do this evaluation, just confirming that your prediction that you have here is actually much better than, you know, the prediction that you have here, because you do need to have a stopping criteria.
Yeah, you should have a much smaller residual then, and then you pass that residual down to check out which other features would help there.
Okay. Just another interpretation by residual in this this context. What do you mean? You mean the remaining?
So if you, let's say your original data, your original label was Y, right?
Yeah.
And your regressed model is YM. So
yeah.
Y minus YM is the residual. So
okay, so it's the standard definition. Okay.
Yeah.
Okay.
So it looks to me like there's an order of you can reduce the order of the computation using that approach. But it looks that way on paper. It would be nice to actually do it both ways and see if it's true.
Oh, okay. Yeah, I think I might just need to brush up on the concept of homogeneity. And see whether it can actually fit into this context.
Okay, great. I think I'm taking too long on this one. Thanks for that. Thanks, Pilani.
Okay, thank you, Prof.
Pardon me, my mic was on mute. Would there be any other questions for Pilani? If there's none, we can have short comments on the presentation itself, since we're running behind time.